In this video, we will look at a few concepts from information theory, like entropy and information gain, that are used in machine learning algorithms such as decision trees and Bayesian inference. In information theory, the basic unit of information is the bit. Bits are used to measure the quantity of information required to encode an event. A classic example is a fair die with 6 possible outcomes of equal probability. So, for instance, for the event that the die equals 2, the probability is 1/6. The number of bits of information contained in this outcome is logarithm base 2 of the inverse of this probability, which is log base 2 of 6, or 2.58 bits. Note that in this context we can have fractions like 0.58 bits, because these are measurement units, not physical transistors or data types in a programming language. By contrast, for an unfair die, for which the probability of 2 is 1 in 5, the number of bits of information contained in this outcome is only 2.32, so less than before. Note that the more probable an event is, the fewer bits of information are needed to represent it. In the extreme case, where the die always returns 2, the event has probability 1 and 0 bits of information are required. This is a scenario in which everyone already knows what the result is without having to check the die, so no additional information is needed. On the other extreme, where the event has probability 0, in other words, it's an impossible event, information cannot be calculated because log base 2 of 0 is undefined. An intuition here could be that we cannot measure information for something that doesn't exist. We can plot the number of bits of information relative to probability. So, for instance, when probability is 1, we have 0 bits as we've seen. At 0.5, we have exactly 1 bit. And as we approach p equals 0, the number of bits required grows to infinity. Entropy. The entropy of the random variable x is defined as the average quantity of information required to transmit every value that the variable can take. Going back to the fair die example, we can calculate the information for each possible outcome. When the die comes out 1, the amount of information we get is 2.58, as we've already seen. When it comes out 2, the information is exactly the same because the probability is the same. Likewise, from 3 to 6. Since the information is the same for all outcomes, the entropy, being their average, is also the same. But if we take an unfair die, where 6 is more probable than it should be and 1 and 2 are less probable, then for 1, 2, and 6, the information will be different than before. So if we want to calculate the entropy, we will have to use the formula. The weighted average information is the probability of the first outcome times the information of the first outcome plus the probability of the second outcome times the information of the second outcome, and so on until the sixth one, which works out to approximately 2.41. Note that this is strictly less than the previous value of 2.58. In fact, the case where all outcomes are equally likely has the maximum possible entropy for a six-sided die. Because of this, we can also think of entropy as the state of disorder, randomness, or uncertainty, similar to the entropy from thermodynamics. Any unfair die will be more predictable, more ordered in a sense, and will therefore have a lower entropy. The higher the bias of the die, the lower the entropy. When we reach the extreme case where one of the probabilities is zero, a special convention is used. As we've seen, the information cannot be calculated because log base 2 of 0 is not defined. This means that technically entropy is not defined either. But 0 times log 2 of 0 is taken to be equal to 0 because the limit of this expression is 0, which allows the entropy to be calculated even if some of the information cannot be. Specific conditional entropy. Conditional entropy helps us use a second variable to get information on the first. To use a simple example, let's consider an urn with 6 balls colored green and blue. We draw one at random and we're trying to predict its color. We can model the color as a random variable and we can calculate its entropy as before. Since there are 3 of each color, the entropy will have the maximum possible value for 2 outcomes, which is 1. But if we consider a second random variable, for example, the size, and we already know that the size is large, then the entropy of color, given the size, is the entropy of the group containing only 2 blue and 1 green. So approximately 0.92, strictly less than the original entropy of 1. This is called specific conditional entropy, since it represents the conditional entropy of x for a specific value of y. Conditional entropy. We can also calculate the other specific conditional entropy, the entropy of color, given that the ball is small, which also happens to be 0.92. So originally the entropy of x was 1, meaning that we had a 50-50 chance of extracting a blue or a green ball. But if we know the ball to be large, the entropy decreases to 0.92. In other words, we are twice more likely to extract a blue ball than a green one. Alternatively, if we know the ball to be small, the entropy also decreases to 0.92. So we are twice more likely to extract a green ball than a blue one. What is interesting here is that it doesn't matter if we know the ball to be large or small. As long as we know what size it is, the entropy of x decreases. And this is exactly what conditional entropy is: the weighted average of all the specific conditional entropies. Since these are already calculated above, all we need is to plug in the weights, which are the probabilities that the ball is large or small. So the conditional entropy of x given y is 0.92 bits. In other words, if we knew the size of the ball, the entropy of color would decrease from 1 to 0.92. Information gain. Since the conditional entropy is smaller than the original entropy, we can say that the y variable helped us gain information about x. This is particularly useful in classification problems. If we need to predict a car accident, for instance, we need to find if something like the weather is a good predictor. This difference between the entropy of x before and after we know the outcome of y is called, unsurprisingly, information gain. In this case, the information gain for x and y is 0.08, meaning y, reduces our uncertainty about x by 0.08 bits. If this number is 0, then the two variables are independent, so knowing the size of the ball would have no effect on the probability that it is blue. I hope this has been useful, and please check the links in the description for additional references. Have a nice day!